Welcome to Leetcode Solver. Today we are going to solve 27th problem in 30-day lead coding challenge, and the problem name is Maximal Square. Given a 2D binary matrix filled with zeros and ones, find the largest square containing only ones and return its area. Largest square. Square means the same side, and there is no any other explanation. The size of the matrix, how big it could be. Okay, in that case, let's think about what will be the brute force approach. The brute force approach will be like fixing the starting point of the grid. I mean, top left of the square and bottom right of the square, and then after iterating over whole elements in that box and seeing whether all those are ones or not. So in order to fix these 2 points in a matrix, we need to iterate 4 times to fix both coordinate of a matrix, and so that we will fix the 4 points. Like if we have to fix two different points like AB and CD in 2D matrix, then we can fix it through both A and B are variable, C and D are variables. So in order to fix these 4 things, we need to iterate 4 times. So and now given 2D binary matrix, okay. Now if we have to iterate over everything within this grid, so it will be a sub matrix, then we have to iterate over again. So we have to use another two loops, another two variables like I and j to iterate over sub matrix formed by above fix. So we have to have another two variables to iterate over the given submatrix. Then after we will see whether all the elements are all elements in submatrix are 1 or not. If all are 1, as well as the fix we made, we will try to match the fix with the square. So we will fix this as square size. That means the difference between A and C will be equals to the difference between B and D. So considering we can also say absolute difference, or we can say C, if C is greater, C minus A, and uh, if D is greater than D minus B. So also we can take absolute difference. So if both sides are equal, we fix that, and then after we will use two variables to iterate over that submatrix and see whether all are ones or not. If all are one, then we will see that this given matrix is a is a submatrix containing ones only, and we will try to do that for every submatrix of square size, and we will return the largest square by multiplying this C minus A into D minus B. So by this way we will calculate this area. Now the complexity, as there is no any constant, let's try to optimize as much as possible. So here we are iterating over, like we fix AB, this is AB coordinate, and this is CD coordinate, and we iterate over this submatrix. We found that this is a square. We fixed as a square, and we found that all these elements are 1. So this is a valid square. If this is a valid square, we will find the area of this valid square, which is this is 1 and 2, and this is 2. 2 multiplied by 2 is 4. So this is basically answer will be, in this case, answer will be equal to C minus A plus 1. So multiplied 2 times, square will be oh sorry, not 2 times, multiplied by the same value. Well, this will be the area, and we will try to maximize every possible area. Well, in this scenario, the time complexity of the solution will be big O of n to the power 6, as we are using 6 for loop to calculate the solution. Let's try to optimize a little bit. We can optimize a little bit, like in order to find whole submatrix contains 1 or not. Instead of iterating over the submatrix, we can simply store the summation of a submatrix starting from 1 1 0 0 position to up to xy position. So we can cal pre-calculate previously calculate store summation from position 0 0 to xy. So we can pre-calculate this summation, and every uh, point at xy we will have a summation from 0 0 matrix to xy matrix. So matrix or submatrix sum, prefix submatrix sum. So if we have this summation, then we can easily calculate the summation at AB by just subtracting the taking the whole summation and then subtracting the other intersections. Like we took whole summations starting from 0 0 to xy point, then as we are interested up to this point, then we will simply remove the summation up to this point, the up to this point, and then after we will remove the summation up to this point starting from 0 0. And in this process we are removing this summation 2 times. So whatever the value over here index, so we will, as we are removing 2 times, we will add 1 times. So by doing so we will have the summation up to this submatrix. So we can do that, and by doing so we will save our last two for loops. So basically we will get it big O of n4 time complexity. Well, can we optimize further bit? Well, we may optimize further, like what we can do. Well, in the same process we can do, like we can use two for loops to fix a position AB, say, and we can use another for loop, third for loop, to fix a position for uh, suppose C. We use a third position C, Okay, we calculate AB and we use another variables to fix C. Then as we know that we have to calculate the submatrix which should be square. Then the we can determine the D. We can easily determine D, which is equals to our C, which is equal to our B position plus the difference in between them. So which is basically C minus A. So this is the D. This should be D. So in this way we can use only three for loops to fix ABCD. So in this way we use three for loops. So we have complexity would be big of n cube. Now can we optimize furthermore? Well, we can optimize a little bit more where we will fix AB and we can do a binary search to find the third value C, because the binary search property uh, here exists a binary search property because as from AB as the length grows, the if length is 1, we see that there exists only one. So the we should always fix AB, which will contains 1 in there in its position. Then if we are considering square of size 1, then it is true. So we can have square of size 1 for sure. And we may have square of size 2 if we fix C, which is uh, equals basically A plus 1 size, and we will check whether the all the values in this submatrix are 1 or not. So if all of them are 1, then it will give us true. Now if we want to have submatrix or square of size 3, then we should choose C, which is should be equal to A plus 2. Now in this case, if this is true, only then the square of size 3 will be true. If this is not true, then square of size will not be true. So if it is true again, then we can go to 4 and we will calculate the C in the same fashion. So we will keep on doing so. We can do that and we can break whenever we get this is false, then we will just break. This is one optimization. Like as we see, this is of one size, which is true, and this is of two size, which is also true, and this is of three size, which could be true as well. But if three size is true, then definitely two size will be true. Two size will be of square as well. And if two size is square, we can see the two size is square here. So definitely the square, this is a AB position. So the square of size 1 will also be a square. So we can see the property that it is always mm, increasing uh, and like true, so which is going fine, and if false occur then it will be false. So we can easily determine the left half and right half interval of the binary search, and we can decide where to go in each partition of our binary search. That's why the binary search property exists here. And yeah, if if the size 4 is false, then whatever the size like 5 6 every all other size bigger size will be false. And we can definitely do a binary search over here to fix the C. and find the maximum possible CH possible, which is true. So basically we'll partition, we'll fix the we'll do a binary search over the length. So this is binary search over length, over length of square, and we'll first fix AB with two iteration, and then binary search over length to determine the square. So if we fix the binary search, if we find the length, then we can easily find it using this pre-calculation. So this pre-calculation will give us answer in big O of 1 complexity. So we will always use big O of 1 complexity to determine the summation of all the values in the square in any submatrix, which is can be calculated mathematically using this submatrix summation. Well, mm, so if we do this, then our complexity would be big O of n square for sure, multiplied by uh, log of n. Well, can we optimize further? As there is no any constant for the uh, given length or size of the matrix, so let's optimize as much as possible. So we came up to big O of n square log n solution. Can we do better? Well, we can do better. Like for each row, we can treat the column summation as the size of each index in this particular row represents size of the column. So here we have 3. This represents 3 size column, and this represent 2 size column, and this represent 2 size column. So what we see that this is 3 size column, 2 size column, 2 size column, and these, if we consider these three cells or three columns, then we can see that we can have this area is common. I mean, they have some common area over there, but this is kind of a rectangle. But as we are considering only this is a rectangle, but as we are considering only square, so we will take the size which is the smallest. So 2 is the smallest and 3 is the bigger size. So we take the 2 and we calculate the square by doing this. So what I mean to say is, like, for every row calculate column height, calculate, suppose the variable x equals column height, or h equals column height for every row in every position. Calculate h, which is equal to column height. If we have column height, then we see a property that if we have column height, then if we determine that what is the largest submatrix, uh, what is the largest what is the largest submatrix we can have using this column height, or what is the largest area we can have using this column height. So if we use column height over here, let's determine for this row we have 1 0 1 0 0, so which is basically the height of each column, which is basically the height of each column. So well, for this case we see that the height is 2, and here the height is 2, and here height is 1, here height is 1. So basically we will have a height uh, the square of size 1 from here as well. We can form this submatrix as the largest area, which is of size 1 by 3. So basically as we are forming the square, we have to consider the size 1. And yeah, so let's move to another column, another row. Here in this row we see that this is 3, this is 1, 3, 2, 2, 2, and we can see that easily it is 2 to 2 is common. We can form this submatrix as a largest rectangle, but the size of the rectangle is, we can see the size of the rectangle is 2 by 3, so we consider 2, so we can form two size submatrix of square. Well, if we go to this row, then we see that the size is 4 0 and 0 and 3 and 0. So we cannot form any submatrix starting from here, because 0 0 is preventing these three to make a square or make a rectangle. So 4 is also here, so these 0 are preventing to form a grid, a submatrix which can form a largest rectangle, but the 0 are preventing. So now if we do this, then we can achieve our complexity. We have to just iterate over whole uh, iterate over this matrix once, so the complexity can be reduced to big O of n square. And for every row we can achieve this largest rectangle in relying or in every row. We can calculate in big O of n complexity or big O of column size, and we can find this height by doing some pre calculations, like by adding the cumulative summation for every, we can maintain the cumulative summation for every columns, and we can just add them based upon what was the previous value, and just if it is 1, then we'll just increase that cumulative summation. In this way we can find this column height. So we are mentioning n everywhere, so these n are basically means the size of the row, considering the n is both the row and column have the same uh, almost same uh, size, so we are referring n as a maximum among both row size and column size. So we can say this as n, then we can have this time complexity over here, time complexity calculation. So this is the least possible time complexity we can achieve, big O of n square, or we can also simplify big O of n square to make it big O of n cross m to make it more clear, where n is the size of row size and m is column size. So in this way we can achieve. Now in order to calculate the column size, I already mentioned that we can column height, we can have a cumulative column, we can maintain cumulative column summation. And now in order to calculate the largest rectangle in relying on particular row based upon the column height value, we can apply a uh, methodology where we can store these values in a stack, and basically this stack will hold the obstacles for every position in every column index. Like, say for example, if we are having maintaining for these values, let me write down this value as column height is 3 and column height is 0, 3, no, no, 1, 3, 1, 3, 2, 2, 3, 1, 3, 2, and 2. Okay, if we are maintaining this, then we can have a stack which will store the um, position where the obstacle was before. So we will just store the obstacle. So here we can have initially there is nothing, and when we goes over here we have nothing, so we'll just store 0. And when we come to this position, we see that this is 1, and the height that was in our stack is 3. So we can easily cover 3, so we can take 3 from 1 as well, because if we want to put 1 if we were to include 1 in our solution of a largest submatrix or rectangle, then we can take 1 for one position. We can also take 3 as well. So as we can take 3, we will just remove it. We will just store blockers in our stack, so we can simply remove that 3. So we will remove 0 and we will store 1 now. And if we go here, because as we can see, like, why we do this, because 1, for in case there was 1 can easily, like, 1 can easily be included in this submatrix creation, I mean the subrectangle creation, because 3 is of higher, which have a higher uh, height. So as 3 has higher height, then we can definitely include 1 along with 3. And if I exclude 3, like just pop out from the stack, then it's also fine. Like, it will not be it will not lose, or it will not impact other values which are remaining values. So let's say if it is of greater height, then we are removing. That means the value the next to the just next right to the 1, if the value next right to 1 is uh, if it is greater, then the blockage for that value will be itself, because this is a smaller value. So this will be blocker for the current ith value will be blocker if the value next to I is greater. And if the value uh, next to I is smaller, then the value at ith position can support that particular value which is next to it. So the I current value I position itself can support, and what about the value that can be supported is the value that was supported for one as well, supported for this position as well, which was already removed, and we were putting the boundary that will block that one. So if the particular index which blocked one is then we have that index, then definitely with the next position will be interested in that index and not to other index which were not a blocker to that value. So that's why through the induction we can maintain this property and move ahead. Let's move ahead. We have one in our stack, and we can also maintain a what was the blocker and for every index. So for 3 we saw that there was nothing, so we put 0 as blocker. So left blocker, say left blocker, so 0 as blocker here, and this is stack actually. We'll calculate both left and right blocker and we will find out the area easily. So this is left blocker, and for 1 we see that there is uh, the only thing that is we popped out everything. So for 1 the only 0 is a blocker over here for 1 as well, because we popped out everything. And if we go to 3 position, we see that in the stack there is 1 remaining. This is basically index. So although the value is 1, we can have, say, maintain index 0 1 2 3 4. These are basically index. So now in our stack we have 1 index, and 3 sees that the value at this index 1 index is 1, and which is smaller. So we see that this is blocker to this 3. So we put 1 as a blocker, 1 position as a blocker. And if we move ahead, we see that there is a 2, 1 as a blocker, and we also put this index 2. And if we move around, we see that there is a 2 available, and 2 will look at the top of the stack, which is 2, I mean which is of the value at second position is 3, and which is not a blocker to 2, so it will just popped out that. And it will look at index 1, and in index 1 there is 1 which is blocker to 2 as well, so it put 1 as a blocker, and while moving it put itself in the stack, and it will goes to the, now we will move to the next index. We see that there is a 2, and 2 will look at the top of the stack, which is 3, and in third position 0 1 2 3 we have 2 available, so we can popped out the value. So 2 is not blocker to 2 itself, so if we popped out that value, then we see that we have 1th index, and 1th index we have value 1 which is blocker to 2, and we can have, so blocker is 1 over here. Now this is left blocker. Similarly we can maintain the right blocker as well. And finally this is stack, and finally we have 4 in our stack, but we'll now we will pop out every value in the stack, and we will calculate the right blocker. Say right blocker. If we have to calculate the right blocker, then we have to go from the last position. So last position here is 2 and the stack has nothing, so at this time we see that the blocker 2, there is nothing to do with this, so we put blocker as uh, the last position, which is say n position as a blocker. Or for this as well, we can have this instead of 0. Actually putting 0 is a 0 as an index is fine, but if we actually want to put a blocker, then whatever the value at the before, just before 1 can be considered as a blocker for this both value. So there could be -1 index, which is blocker instead of 0. So -1, we can put this like -1 was blocker, and -1 index was blocker, and 1 index was blocker, 1 index was blocker, in this way. Or we can also maintain the actual blocking point, so actual point where we should stop. Instead of putting the index, we can put the actual point, actual index where we should stop. So for this 0 0, and for this we can take 2 2 and 2. So these are the point where we should stop. After that we could not move to get the submatrix which include a particular position, which is based upon particular index. Like if we consider this index, then maximum left we can go is 2, and if we consider this index, maximum left we can go is 2. Like maximum left we can go maintaining this particular height. So blocker or maximum index we value at ith position can go maintaining height at ith position. You can say something like this as well. So for the right blocker, either we can put n, like as I mentioned before, -1 -1, or we can put simply the index itself as a blocker. Suppose I put n -1 as a blocker to itself, and let's say, and then in the stack we have, now we will have the n-1 position, and it moves here, and it's a 2, and it says that 2 can be 2 will not be blocker, so it will remove that n-1 from the stack. And as it had removed everything, so removing everything will make n-1 as a blocker, and we can now have n-2 in the stack. And if we move to the n-3 or n-2, for n-2 we already calculated. If n-1 n-2 n-3, if we move to the n-3, then it will see at the top there is n-2 which has value 2. So value at uh, n-3 is 3, so this will be particular blocker for this 3. So we'll remove that, and we'll put blocker as n-1 n-2 n-2. So this is a particular blocker, but we will not put n-2 itself, we will put n minus 3. So index itself is a blocker. Index itself will be the maximum index. It can go to the right side. So let's say stack now have n minus 3 and it reached to n minus 4 position, and it says that the value at n minus 3 position is higher than the value at its position. So it will definitely can pop out this value. After popped outing, the stack remains empty. So if it remains empty, then we mean that considering the height at one height, we can go to right up to n minus 1 position. So this makes a sense. Now let's move to other index, which is, and let's put n minus 4 in our stack, and let's move to n minus 5. In n minus 5 we see n minus 4 is there, and we see the value at n minus 4 position, which is 1. And basically we, for 1 we can't do anything, so we'll just treat them as a blocker. So for 3, for 3 to go to the right side, it will this n minus 4 position will not allow. So we'll simply say that n minus 5 itself is a maximum value which we can go. Well, in this way, we'll calculate the right blocker and left blocker, right boundary or left boundary as well. And so a boundary makes more sense over here, as we are actually calculating the boundary, and this is also right boundary, left boundary. Now finally, we'll remove stack every value. As we had calculated everything, now we can calculate the maximum sub matrix for the particular position. So if we go here, then we see the left boundary is 0, right boundary is 0, and n minus 5 is also 0. So we can make a one rectangle of size 3 by 1, and n minus 1 is 4. This is n minus 3 is 5 minus 3 is 2. This is 4. This is 4. Well, if we maintain this, then we see that by just iterating over the every position, this says that maximum right boundary it can go is 0 and left boundary is 0, and for this as well, the maximum right boundary it can go is 4, and left boundary it can go is 0, but the value at its position is 1 itself. So 1 multiplied by 4, 1 will be the height and 4 will be the width. So the minimum angle height and width is height, so we have to consider sub matrix uh, are square of size 1. So now let's move to this position. We see that both sizes 2, so the value at its position is 3. So we'll have a square of size, we'll have a rectangle of size 3 by 1, but square of size 3, square of size 1 only, because the minimum among 3 and 1 is 1. And if we consider this case, it says that it can goes left to 2 position and right to the 4 position, and the value at its position, we see that value at its position is 2, and if we consider 2 value, then we see that 2 and 4 is this, and in this boundary 2 multiplied by 3. So basically the rectangle will be of 6 area, but we have to take only only square, so we will take 2 as one of the height and minimum among height and width. So 2 multiplied by 2 will be equals to 4, and for this case as well we will do the same thing. So we'll have 4 sides square. Let's move into implementation. How we will do that? We have to maintain column height by doing column cumulative summation. Well, let's do it. Vector, let's calculate n and m. N is the row size, if row is empty then we will simply return 0, otherwise we will calculate m, which is equal to matrix 0 dot size. We'll calculate column again. Now let's define a cumulative summation vector. Say column height, we'll calculate the column height over there, so which is of size n by m. Let's put everything 0 initially, and let's iterate over the column wise and calculate cumulative summation. Well, we can just iterate over the row wise and maintain that column height, and after maintaining column height for every row we will do operation. Let's iterate over row. Say it's better to write down actual name. Say r is row is starting from 0 and it is equal n, column starts from 0, column less than m. So now we fix row and column, and now let's calculate column height. Column height of row and column will be equals, if now we have boundary conditions, if this is for first row then everything will be equals to the value at its column. So if row equals 0, then it will be equals to matrix value at RC position minus 0, which gives the integer value. So this is a character matrix, so we subtract one character to get the integer value. Otherwise, if we have row is 0, then we can calculate by doing this. Otherwise we can simply say whatever the value we have in our column. So we have 3 conditions over here as well, so it's better to write the if else condition. Say if row is 0, then this is equals to matrix of row column minus 0 to make the integer. otherwise else we have two things to do. If matrix row column is equals 1, then what we have to do is column height row column will be equal to column height row minus 1 row minus 1 column. We have to take this and add 1. Otherwise, if it is not value 1, then the value column height will be remain 0 as it is. This is not actually cumulative sum. This is basically we are maintaining the height, because if we get 0, then we are not considering previous summation at all. So for 1 we are only considering cumulative summation. So I think everything will be fine, and by iterating over this we will maintain column height for r row, and now we can calculate these things that I described over here, which will return me the solution maximal square. So let's calculate, and for every return value we have to maintain the final answer, which is let's say 0 initially, and we have to maximize final answer with the maximal square size we will be getting. So max square size in a row. So we will pass column height r, which is a vector. We will pass this vector, and it will give us return a integer, which is the maximal square size, and finally we will return answer. Now let's define this method, which will accept vector as an input parameter, uh, say reference. So vector will be column height vector, well. Now let's define stk stack. Now let's define the values we have to maintain, left and right values that I defined, left boundary and right boundary. So let's calculate let's first calculate size of the column height, and vector of left boundary, which is of size n, and say initially we initialized as a 0, and let's iterate over given vector of column height, and let's find the largest maximum square size we can. Square size, actually it should be square area, maximum square area in a row, which is required answer if we consider every row. Now let's see if stack size is not empty, and we see that there exists a top value stk dot top basically stk.top will store index, so the value can be found by column height of stk.top. So we have something, and the column height stk.top, this is something, some values over there, and if we found that this value is greater than current value, column height, current height of I, then we'll pop out this value. So stk dot pop will keep on doing so. Now finally, if after performing all those operations, if we found that stk dot size is 0, that is stack is empty, if this is the case, then left boundary of I will be 0, as we are saying boundary, not obstacle position. So left boundary would be 0. Otherwise, what will be the left boundary? Left boundary will be equal to whatever the value at the top, stack dot top, and the value will be the index just before this. So this is a obstacle index. So we'll add 1 to the obstacle index to find the boundary. We'll add 1 to the obstacle index. So in this way we found a boundary. Now let's clear while not stack dot empty. We'll clear every entry to the stack. So stack dot pop. Now let's calculate the right boundary. We can do that just iterating over this. We don't need to maintain the values in left boundary like right boundary metric vector. We just iterate and find the area. So let's say area is equal initially 0, and just we will iterate from the back side. We will do the same thing like stack size. Stack has some size, and column height of last index is greater than particular or current column height. Then we'll pop out that values. We don't need this anymore. If we found that stack dot size is equals 0, say let's write boundary so if size is empty, then it will be equal to right boundary. If it is not 0, then we will calculate right boundary equals stk dot top minus 1. So we find the actual index which is right boundary. Now as we have calculated index, now in order to calculate the size we have to add, like subtract those and add 1. Well, we can found column and height, width and height. So let's say width is equals to right boundary minus left boundary plus 1. And we have to find the minimum among width and height to get the square. Well, area equal to maximum of area, comma, we have to find minimum one. So let's find square size equal to minimum among width and height. So height is equal to column height I. So square size multiplied by square size will return area. Well, looks good. Let's run the code and I hope it will compilation error. It will give at line number 27. Right boundary. Your answer is 16. Answer is 4. Okay, let's see what went wrong. Everything is 0 initially and we did it over nm. If row is 0, then column height will be equal to value at that particular position. Otherwise, matrix RC will be, if it is 1, then it will take previous one, R minus 1C, and if it 1, otherwise it will be 0. Column height R. Okay, we forgot to put value in the stack. Stick that push. Let's submit. Wrong answer. Okay, the sign should be greater than or equals. Let's try. Well, it is accepted. Let's see more details. 44 millisecond, 10.2 megabyte. Still, you are 9.5% of CPP solution. Still, it can be improved. Well, this is a big of n square solution. Time complexity and space complexity is also the same because we are maintaining column height. And yes, thank you everyone for watching this video. If you have any other better solution or any other approaches, any alternative idea in your mind, please feel free to share and comment. Have a nice day.